Welcome to this lecture series in number theory. In this lecture, we will discuss some divisibility tests that we learn as children in high school, but this time we will prove them. So all we will need to know is congruences, although this is not strictly necessary or not at all necessary to discuss what we are going to discuss, but I will use this language because we need to get comfortable with this language. All right, so we will assume that you are now familiar with the notion of congruences and especially modular arithmetic, which says that if we have some positive integer n and we have two integers a and b, they are congruent modulo n, and two integers c and d, they are also congruent modulo n, then you can sum and product while maintaining the congruences. So we discussed this in detail and let's proceed. Some problems for practice. And now let us get started. So let's discuss the divisibility rule by 4. So suppose, something has been written here, I will explain, but what do we learn in high school? Suppose I have some number, something like, let's say 736. And I want to know whether or not this is divisible by 4, then we are told that just look at the last two digits. And if that number, the number that you obtain by ignoring everything else, is divisible by 4, then the whole number is divisible by 4. 36 is indeed divisible by 4, so therefore 736 is also divisible by 4. All right. Why is that? Why is that true? It's a very simple thing. So the thing is, 736 is what? So I'll write it here. So 736 is just a shorthand. When we write 736, what do we mean? We mean 7 into 100 plus 3 into 10 plus 6. That's what 736 stands for. So this is divisible by 4 if and only if this is divisible by 4. But this is clearly divisible by 4 because 100 is divisible by 4. So in congruence language, 736 is congruent to 0 plus 3 into 10 plus 6 mod 4. Which is same as 36 because 3 into 10 plus 6 is 36. So it just says that this is divisible by 4 if and only if 36 is divisible by 4. That's all. That's the proof of what I've written. But what have I written? So when I write something like this, what I mean is that these are all numbers from 0 to 9. And this just denotes, this is my definition. This just means ak times 10 to the power k plus, I will run out of space, so I will write it here, plus dot 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 a1 times 10 plus a0. Right, so for example, you can take this as a2, that as a1, and this as a0. Right, this is a2, 3 is a1, and 6 is a0. So strictly speaking, I should have written it like this for it to match with my notation. But when we write something like this, it is implicit that we are using the decimal representation. Decimal stands for base 10 because deci is 10. Right? So, that's, I don't want to say too much about it. So when is this number divisible by 10? Same as saying when is this number divisible by, not by 10, sorry. When is this number divisible by 4? If and only if this number is divisible by 4. But this number is congruent to, this is congruent to 0 plus 0 plus dot 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 plus a1 into 10 plus a0 mod 4, which is congruent to this number, because this thing is exactly that number. So what we have shown is that the given number leaves the same remainder as the number formed by the last two digits of the given number, modulo 4, of course. So this is divisible by 4 if and only if the number formed by the last two digits is divisible by 4. As simple as that. But from here you can also get a more convenient divisibility criterion, because this thing is also congruent to, I could have written, let me write down what I'm trying to say. So what I mean is this number is congruent to 2 times a1 plus a0 mod 4. Why is that? Because this is congruent to this mod 4, but this is congruent to that mod 4, because 10 is congruent to 2 mod 4. So this number is congruent to that mod 4. That's it. Once you realize that, you do not need to really talk about the number formed by the last two digits. You multiply the second to last digit by 2 and add the last digit to it. If that number, which is certainly smaller than this thing, easier to check if it is divisible by 4. So in case of 736, 2 times 3 is 6, plus 6 is 12. 12 is certainly divisible by 4. Okay, great. Divisibility by 9. So this time, suppose again we have a number with k plus 1 digits written in base 10. Then that number is divisible by 9 if and only if the sum of all the digits of the number is divisible by 9. This is also something that we learn in high school. So for example, I have something like, again, 736. If I sum all the digits, I get 9 plus 7, 16. 16 is not divisible by 9. So the number is not divisible by 9. But what is the proof? The proof is, as it was, this number by definition is equal to, but I will write congruent to, right? But this thing is congruent to what? This is congruent to ak 1 to the power k plus, so what have I done? 10 to the power k is congruent to 1 to the power k, modulo 9. Why? Because 10 is congruent to 1 modulo 9, and we can exponentiate both sides by non-negative powers. So the first term is congruent to that. Similarly, the second term is congruent to that thing. And this is nothing but the sum of all the digits. That's it. Very simple. Let's see one more. It's more complicated. So suppose again we write a number in its decimal representation, then the number is divisible by 11 if and only if the sum of the digits but with alternating signs is divisible by 11. So what about 736? 736 is, if I sum up the digits with alternating signs, I get 10, which is not divisible by 11, so this number is not divisible by 11. What is the proof? The proof is the same as the previous thing. You just write the number. Let me be a little bit short. So this is congruent to, maybe I'll write it this way, just a shorter way to express the same thing. So this goes from 0 to k, ar, 10 to the power r. That's exactly what this thing is. Modulo 11, they are equal, but I will write modulo 11. But now I'll use the fact that 10 is congruent to minus 1 modulo 11. And that's it. This is exactly, this whole thing is exactly the sum of the digits of n with alternating signs. That proves divisibility by 11. All of this could have been said without resorting to the language of congruences, but using the language of congruences certainly reduces the length of the proof and also makes things much more clear and neater. Arguing this without using congruences would lead us to using binomial theorem here. You will write 10 as 11 minus 1, use binomial theorem, this, that. All it will do is obscure the simplicity of it. Alright, so I think this is all that I wanted to say. As usual, like, comment, share, subscribe, and I will see you next time.